Lecturer, Ismail A. Mustafa. The comprehensive role of the geologist in the oil industry. 1. Exploration phase. Exploration geologist. In this phase, the geologist acts as a detective, searching for where oil might be hidden. Seismic interpretation, analyzing sound waves reflected from underground layers to create 3D maps of the Earth's subsurface. Basin modeling, studying the geological history of a region to ensure the presence of the petroleum system elements, source rock, reservoir rock, seal, and trap. Prospect generation, identifying the best locations to drill the first exploratory well, wildcat well. 2. Operational phase, well site geologist. Once drilling begins, the geologist moves to the field to monitor the well in real time, and others tasks. 1. Lithology. Logging. The geologist maintains a master log to record the exact rock types being drilled meter by meter. 2. Pressure monitoring. By analyzing the rate of penetration, ROP, and cutting shapes, the geologist identifies overpressure zones. 3. Early warning. The geologist warns the driller to adjust the mud weight to balance the underground pressure, preventing dangerous gas kicks or wellbore collapses. Cuttings analysis. Examining rock fragments brought to the surface by drilling mud under a microscope to identify rock types. Lithology. Hydrocarbon. Shows using ultraviolet, UV, light to detect any traces of oil or gas in the samples. Casing point selection for oil well design. Deciding the safest depth to set the casing to protect the wellbore, mud logging supervision, monitoring gas levels and drilling parameters to ensure safety and prevent blowouts. 3. Formation, evaluation, and petrophysicist. After drilling, electronic tools, logs, are lowered into the well to measure physical properties. Porosity. Calculation. Using the, for example, density log tool to determine the storage capacity of the rock. Saturation determination. Calculating the percentage of water versus hydrocarbons, oil, gas, within the pores. Net pay identification. Determining the thickness of the rock layers that are capable of producing economical quantities of oil. 4. Laboratory analysis. Core analysis. The geologist studies core samples, cylindrical rock samples, to get the petrophysical properties. Routine core analysis, RCAL. Precise laboratory measurement of porosity and permeability, the ability of fluids to flow through the rock, etc. Special core analysis, SCAL. Studying wettability, the preference of the rock to be covered by water or oil, and capillary pressure, etc. 5. Production and development phase. This is a high-level role where the geologist manages the life of the oil field. 3D static modeling, building a digital twin of the oil reservoir to visualize how layers are connected. Infill, drilling, identifying bypassed oil zones to suggest new locations for production wells. Enhanced oil recovery, EOR. Studying reservoir heterogeneity, barriers or faults, to plan water or gas injection strategies to push remaining oil to the surface. Reserve estimation. Calculating the total volume of stock tank oil initially in place, STOIIP, to determine the field's economic value. 6. Role in enhanced oil recovery, EOR. When the natural pressure of the reservoir declines, the geologist intervenes in injection operations, studying heterogeneity. analyzing geological barriers, such as faults or shale baffles, that might prevent injected fluids, water or gas, from reaching the target zones. Mapping injection paths, ensuring that the injected materials, steam, CO2 or chemicals, move in the right direction to effectively sweep and push the oil toward production wells. 7. Risk assessment and reserves estimation. This role bridges the gap between geology and economics. STOIIP. Calculation. One of a geologist is estimating the stock tank oil initially in place, the total volume of oil underground before production starts. Geological risk analysis. Calculating the geological chance of success, GCOS. To protect the company from massive financial losses by evaluating the probability of a dry hole. 8. Digital geosciences and artificial intelligence, AI. In the modern era, the geologist acts as a data scientist, like digital rock physics, DRP, utilizing high-resolution CT scans to create digital pore models and simulate fluid flow numerically, saving time and costs compared to traditional lab work. Machine learning. Integration, training algorithms to predict rock faces or petrophysical properties in data-poor wells by leveraging data from neighboring data-rich wells. The role of the geologist in clean energy and energy transition. 1. Underground hydrogen storage, UHS. Hydrogen is a key fuel for a carbon-free future, but it requires massive storage space. Geologists lead this effort by reservoir selection, identifying salt caverns or depleted gas fields that can safely store hydrogen at high pressure. Biochemical assessment, studying how hydrogen might react with underground minerals or microbes to ensure the purity of the stored gas. 2. Carbon capture and storage, CCS. To combat climate change, CO2 is captured and injected back into the earth. The geologist's role is critical for site characterization, selecting deep saline aquifers or mature oil fields that can permanently trap carbon dioxide. Seal integrity, ensuring that the cap rock, seal, is strong enough to prevent any gas leakage back to the surface for thousands of years. 3. Geothermal energy. Geothermal energy involves extracting heat from the Earth's interior to generate electricity. Geologists contribute by thermal mapping, identifying hot spots where high temperatures are accessible near the surface. Fracture characterization, studying the permeability and natural fractures in rocks to ensure efficient circulation of water or steam to transport heat. 4. Exploration for critical minerals. Clean energy technologies, like EV batteries and solar panels, depend on minerals like lithium, cobalt, and rare earth elements. Geologists are responsible for mineral prospecting, using geochemical and geophysical techniques to find new deposits of these strategic minerals. Sustainable mining, planning extraction methods that minimize environmental impact.